Hello students, welcome back. We're going to continue with Carbohydrates Part 9. Carbohydrates Part 9. In this video, we're going to look at some more glycosides. Specifically, we're going to look at several common disaccharides. And what you want to remember is all monosaccharides that come from aldoses these are going to be hemiacetals. And if the aldose forms a disaccharide, then it's going to become an acetal. That's a good thing to remember. And so all of the disaccharides that we're going to make will become acetals. Okay, let's start with, we've already looked at maltose. This is glucose. Well, let's just go back to it. Yes, we have maltose. We've already looked at maltose. Maltose is just a disaccharide that has an alpha 1,4 bond. An alpha 1,4 bond. The next we're going to look at another disaccharide, but it's going to be a beta 1,4 linkage. It's going to be, we're going to have two glucose molecules. Okay, 1, 2, 3, 4, 5, and 6. CH2OH. Up, down, and this is going to be beta, so we'll put this one up. So I'm going to go ahead and put all of my hydrogens here. Sometimes I put the hydrogens, sometimes I don't. And so this is beta D glucose. And we're going to have another one of those. So I'm going to draw another beta D glucose. Well, I'm going to draw another D glucose. And I'm going to do something here to show that it doesn't matter what this second anomeric carbon is, because I don't want you to get confused. I don't want you to let that confuse you into naming. H, H, H. Now for this last one here, I'm just going to put HOH for the second one, the one that's going to serve as our alcohol, because it doesn't matter. It's just doesn't matter if that's alpha or beta. And the reason I do that is because I don't want you to let that confuse you in the naming of the glycoside, of the disaccharide. So this is D-glucose. And we don't care about the configuration of that anomeric carbon in there. Okay? And so what's going to happen? This anomeric, the 4-hydroxyl is going to attack the anomeric carbon there. And so let's draw that compound. I should have made the second one a different color. That would have made more sense. But instead of doing it, I'll do this then. I'll make the OH a different color. There we are. And so we're going to end up with 1, 2. I'm trying to go too fast, am I not? 1, 2, 3, 4, 5, 6. CH2OH. Up, down, and now this one is going to go up. I need to show you something. I'm not going to have room on this one, but I'm going to have to show you this. So I'm going to go up to this one, O, and up to my 4 carbon, O. This is up, CH2OH. So that's up, and that's down. This is up, down. And the anomeric carbon, it doesn't matter. The orientation does not matter. And so when we name this, using our convention here, we'll just call this glucose. I'm going to put it here since I have more space here. Glucose Okay. Now we've put the name of the first sugar. Now we need to identify the glycosidic bond. This is the beta carbon. This is a beta 1,4. And now the second glycose is glucose. And that's how you name this disaccharide. And we're going to have an H here. Okay. Now, some things you need to know. This is the anomeric carbon. Anomeric carbon is in the, of course, the beta configuration. This functional group here, which has an OR, an OH, and an R, this functional group is a hemiacetal. However, once you add this sugar to it, now you have, this is an OR, an R, and another OR. This is no longer a hemiacetal. This functional group becomes an acetal. And so all disaccharides, or all polymers of sugars are acetals. They're all acetals. If the anomeric carbon was an aldehyde, they're going to be acetals. Okay? This bond, the bond that we create here, this bond is called a glycosidic bond. This is a glycosidic bond. This entire structure is called a glycoside because it's a sugar attached to an alcohol. The second sugar here, this is our alcohol. And the first sugar here, this is our glycose. And this glycoside here, since it's two sugars, we can also call this a disaccharide. So all disaccharides, yes, if this is an anomeric carbon, all disaccharides are glycosides. Okay. Now this compound, or this disaccharide, when you have a beta 1,4 linkage, its common name is cellobiose. And if you have many beta 1,4 linkages, then we form a polymer of cellulose. And the polymer of cellulose is called cellulose. And so we can't digest cellulose because we don't have any beta 1,4 glycosidases. So we can't digest this. But we do have alpha 1,4 glycosidases. And that's all I want to say about this glycoside, or this disaccharide, in terms of its naming. There's one additional thing I want to say about this disaccharides and any other polymers, even monosaccharides to an extent. Now, if you look at this concept, this is a really tough concept to get, so I want to make sure. Let's do this. I'm just going to draw a monosaccharide. No, I'm going to do that on its own slide because we're just going to stop here. And on the next slide, these ends are different. The ends of the disaccharides are different. Let me get a good color so you can see. This end here, Oops, I don't know how to draw a star. Yes, this end here is different from this end. And I'm going to explain that. I'll do that next. So here we are. Cellobiose, the disaccharide beta 1,4 linked glucose. Okay, on this clip we're going to look at the two ends of sugar polymers. Anything from a disaccharide on, the two ends are different. I'm just going to draw a generic polysaccharide or generic disaccharide here. So here's our generic polysaccharide. This is our I guess we'll do alpha, it doesn't matter. Okay, now on these on this disaccharide rather, this is the anomeric carbon here, and this is the anomeric carbon here. Now this anomeric carbon is involved in the glycosidic bond. However, this anomeric carbon is not. So something can happen here. This can still open up. So we can go from here to this. This is the key, the opening. This can't open up. Okay. I guess I should have put my OH here. Another OH. And what will happen here? This can open up. Now see this, the right, I guess you call it the right end of the polymer. It can be on a disaccharide, trisaccharide, all the way up. But the right side can open up. And when it opens up, it can take oxygens away from something else. And so let's say you have something, or it can give its electrons to something else. I guess that's a better way to thinking of it. So, well, either way you look at it, if this gets oxygens, it could take an oxygen away from another, from some other molecule. And let's say, I don't want to show it that way. I really don't want to draw it because I don't want you to be thinking about this one way. But that's where the concept is, and you have to get that. I'm going to only explain this one way because I want you to just make sure you get it. So let's say you have some species here, something that has oxygen attached to it. And so, and we've already seen this reaction where you can actually, this is carbon 1. Carbon 1 can become oxidized. Okay, I'm going to show that product here. Carbon 1 can become oxidized here. And so it can basically take this oxygen away from whatever this species is. We'll have here O. It can take away this oxygen plus, and then it can leave this, whatever this is, it can relieve it. It can leave it reduced. So this has become reduced, and this has become oxidized. And so, of course, if we just name this monosaccharide and this carbon 1, this would be an aldonic acid. And so this becomes oxidized. And we've already seen that. And that's really not what's important here. That can become oxidized. The important thing is here is that this can open up, and when it opens up, it can reduce something else. And so this end, the right end, or the rightmost anomeric carbon, that end of the disaccharide or trisaccharide or polysaccharide, this is called the reducing end. The reducing end. And it's called the reducing end because it can open up, that chain can open up and reduce something. It can take oxygens away from something or give electrons. But I just want to explain it one way. However, this end over here, let's say this were like this oxygen was down. This can't open up. There's no way this can become an aldehyde. It can become an aldehyde. So this end can't reduce anything. So this end is called the non-reducing end, because there's no anomeric carbon over here. It can't. That ring can't open up. And so whenever you have any polymer or an oligomer of a sugar, the end that the anomeric carbon on, that's called the reducing end, and the other end is called the non-reducing end. There can only be one reducing end in a polysaccharide because there's only one anomeric carbon remaining. There can only be at most one reducing end. Now, if both anomeric carbons come together, if the bond formed between two anomeric carbons, then there is no reducing end. That sugar is a non-reducing sugar. So that's the key here. The reducing end is the end where the anomeric carbon is. The anomeric carbon opens up to become an aldehyde, and then that aldehyde can take an oxygen away from some other species and reduce that species. And so this is the oxidized species. This is the reduced species. And for that reason, this end is called the reducing end. So you have two ends of sugars, the reducing end and the non-reducing end. And the reducing end is on the end with the anomeric carbon. Okay, let's continue with our next disaccharide. And this disaccharide is going to be composed of galactose and glucose. So let us draw galactose here. First we're going to draw galactose. 1, 2, 3, 4, 5, 6. H2OH. And galactose is the 4 epimer of glucose, so the 4 has to go up. And this one is also up. And then down. And we'll have beta. Let's have. And so this is beta. We know it's beta D galactopyranose, but we're just going to put beta D galactose. Okay, and glucose. 1, 2, 3, 4, 5, 6. Up, down, up, down. And it doesn't matter what the orientation of this one is. I'm just going to write that one like this. So what's going to happen here, this is going to be, now it's going to be a beta 1,4 linkage. A beta 1,4. So I'm going to draw something. When I draw this, I'm going to erase the bond and draw the bond another way. So be ready. So if you're writing with a pen, don't write the bond as I've drawn it. So this OH is going to attack the anomeric carbon, and we're going to end up with this. 1, 2, 3, 4, 5, 6. Up, up, down. And so this is going to go up So this bond is going to go up here, and there's going to be our O, and then it's going to attach to the glucose from the bottom. So it's going to kind of go under like that. Okay. Okay, this is glucose. And it doesn't matter what this one is. The orientation does not matter for this one. Now, let's go ahead and name this. The name of this is going to be galactose. Oh, and we didn't put here the name of this one. This is D-glucose. So this is galactose. That's a beta linkage. Beta 1, 4, and then glucose. That's the name of this disaccharide. Remember, this is a disaccharide, and that's to also be a glycoside. Now, bonds aren't drawn with curvy lines. And if you look at the Hayward projection, everywhere where there's a vertex or a corner, that represents a carbon. However, when you're drawing a bond here when you're drawing a bond between sugars, that's not the case. For example, I can draw this here, and you see here we have 1, 2, 3. We have 4 corners, and you think, oh, there are carbons there. But in bonds, corners are not. Corners in glycosidic bonds, in bonds between sugars, corners are not carbons. So I'm going to put here corners are not carbons. And so we just draw the bonds that way so that we can keep it just makes it easier to draw disaccharides. You can keep the two sugars at the same level and just make the bond fit. And so this just shows you that this bond is going up here, so this is a beta bond, and this 4 is going down so that you will have glucose. And so this is galactose. This is galactose beta 1,4 glucose. Now this sugar is also known as, now this is a beta 1,4 linkage. There are not a lot of beta glycosidases in the body, so we have to have something very special for this. This is a very special sugar. And so this sugar, let me explain it to you this way. This sugar is found in the milk of mammals. In the milk of mammals. And the young only produce conventionally, the young, in most mammals, the young only produce this milk sugar. This is called milk sugar. The young of these mammals only produce this milk sugar while they're young, while they're weaning. Once they get to be adults, they don't produce this sugar. They don't produce the enzyme that breaks this sugar down anymore. And so young only produce the enzyme that breaks this sugar down when they need it. Let me give you some I need to give you some general terms now. Okay, this bond here is called a glycosidic bond, of course, because it's between 2 glycoses. This is a glycosidic bond. And the name of the general enzyme which breaks this bond is a glycosidase. So the enzyme here would be a glycosidase. That would be the name of the general enzyme that breaks this bond. Now, this disaccharide here is a glucosyl galactoside. It's a glucosyl galactoside. And so it's this sugar. The first sugar in the bond is what you name the glycoside after. And so this is a galactoside. And so the specific enzyme here would be a galactosidase. And so the enzyme which breaks this bond would be a galactosidase. And because this bond is going up here, it's going to be a beta galactosidase. And so mammals, when they are young, they produce this enzyme, beta galactosidase, which breaks down this milk sugar. Now this milk sugar has another common name, and it's called lactose. Lactose is the name of this milk sugar. And as I mentioned before, in most mammals only produce this enzyme, the enzyme beta-galactosidase, when their offspring are young. Once they get to be older, there's no need because they don't drink milk anymore. However, most humans can produce this enzyme. Well, many humans can produce this enzyme throughout their lifetimes or well into adulthood. And so these humans can digest milk. Let me explain something here, how it works. So what we're going to do here, I don't know. Okay, here we're going to have, I don't know, I'm going to draw this. Okay, here we are. Okay, now this is the esophagus, stomach. I need the stomach to be a little bigger. Okay, here we are, very good. And so what we're going to do now, I want to kind of erase this because I need the stomach to be kind of bigger. So I'm going to make the esophagus very short. This is the esophagus here. And then this is the stomach. There's the stomach. Okay. And these will be, this is our small intestines right there. And then we'll go. Okay, that's our small intestines there. And this will be, we'll make this one bigger. This would be our large intestines. So, when you eat foods, when you eat milk, when you drink milk, I don't have any milk here. Let's just draw milk. So here we have a container of milk. Does the body good. The milk goes in. Then you have the lactose here. And so the lactose is going to pass into the small intestines. You're going to have the lactose. Now, the small intestines are very closely associated with the bloodstream. And so lactose wants to go into the bloodstream, but it can't be. And so you have beta-galactosidase. It breaks the lactose into the two sugars. And then the two sugars individually, they can go into the two sugars can then pass into the bloodstream. And everything is okay if you have the enzyme beta-galactosidase. Some individuals, many humans, let's look at that scenario if you don't have the enzyme and see what happens. And so, here again, we're going to have our stomach here. There's our stomach. We're going to have there's our small intestines here. small intestines, and then we're going to have our large intestines. And so what happens here for these individuals, you get the milk, you digest, well, you ingest the milk, and then you're going to have, okay, there's your lactose. Then the lactose is going to come here into the small intestines. We'll put here SI for small intestines. In the small intestines, there's no beta-galactosidase. There's no beta-galactosidase here. So the lactose cannot go into the bloodstream. And because it can't go into the bloodstream, it continues on and it goes into the large intestines. So now you have the lactose in the large intestines. And this is where the problem occurs. In your large intestines, you have bacteria. We call that your intestinal flora. And so you have bacteria in your small intestines. And the bacteria use these sugars, use this lactose, and it causes it to ferment. And then when it ferments, it produces gases. It produces like hydrogen gas, can you believe that? And things like carbon dioxide and methane, CH4. It produces these gases, and it causes extreme bloating. It causes extreme bloating in your large intestines. Also, because of osmotic pressure, if you have all these sugars here, sugar is like a solute. It's a solute, of course, and so lots of water is going to follow those sugars into the large intestines, and so you're going to have extreme diarrhea. I never know how to spell diarrhea, but I think that's it. It's going to cause extreme diarrhea. And all of this together, all of these problems, sometimes it even causes vomiting. And so it can cause vomiting, regurgitation. It can cause vomiting. And all of this together, all of these problems together, are known as lactose intolerance. And the reason is because we don't have this enzyme here. Let's go all the way back. We don't have this enzyme here, a beta-galactosidase, which is a beta-glycosidase. There are a lot of beta-glycosidases that are found in the body. And so this is the enzyme, or this is the sugar lactose. Galactose beta-1,4 glucose. Kind of hope it makes sense. There's a lot of information about that one.